In the name of Allah, in this lecture, we will explain the practical concept of the delta angle, and we will understand the difference between the power factor expressed as cosine theta and the power factor expressed as cosine phi. We will also clarify whether these angles are just symbols that can be interchanged, or if each angle and each symbol carries a specific meaning. In the previous lecture, I spoke about insulation tests in transformers and explained the insulation resistance test as well as the polarization index test. In the upcoming lecture, we are supposed to explain the dissipation factor test or tan delta test, along with the power factor test or cosine theta test. That is why it is very important at the beginning to understand what the delta angle actually is, in order to comprehend what tan delta means. Also, for as long as we have known, the power factor has been expressed as cosine phi. But why, in the case of the transformer insulation test, did we say power factor test or cosine theta test, and not the usual cosine phi? Of course, everyone knows that if we have a source of electrical voltage, whether it is a generator, a transformer, or any source of electrical voltage in general, and naturally, with the presence of different loads, the electrical current will begin to flow through the cables, wires, or various conductors in the direction from the source to the loads. And of course, since the voltage is alternating and the current is alternating, we understand from this that due to the presence of both the voltage and the current, there will arise between them an angle phi, or the phase angle phi, regardless of the actual shape of the phase angle phi. Meaning that if the loads we have are inductive loads, then naturally the phase angle phi will be negative, which means a lagging power factor. If the loads are resistive loads, then the power factor equals unity because the phase angle phi equals 0. And if the loads are capacitive loads, then naturally the phase angle phi will be positive, which means a leading power factor. Accordingly, we understand from this that regardless of the type of loads, the presence of voltage and the flow of current in the conductor will always create between them a phi angle or the phase angle phi. But it is very important to know that we have two types of current. The first type is the current that flows through the wires or conductors, which is the conductor current. The second type of current is the current that flows through the insulating material, which is the insulation current, also called the leakage current. Accordingly, we can say that the electrical current is of two types: the current flowing in the conductors and the leakage current flowing through the insulating material. For example, consider a cable connected between the source and the load. The current that flows through the conductor is in the direction along the conductor, that is, in the direction from the source to the load. Therefore, the angle phi, or phase angle phi, is the angle between the current flowing in the conductor and the voltage applied to the conductor or the cable. Hence, the power factor is simply the cosine of the angle between the voltage and the current, which equals cosine phi. As for the current that flows through the insulating material, or the leakage current, this flows along the thickness of the insulation, and by length of the insulation, we mean the thickness or the depth of the insulation. For instance, if we have a 66 kilovolts cable, then the highest point at the conductor, or the first point in the insulation, point A, will have a potential of 66 kilovolts. The last point in the insulation, that is, point B, is supposed to have a potential of 0 volts. Accordingly, we find that the current flowing through the insulation, or the leakage current, will flow in the direction from point A, which has 66 kilovolts, to point B, which has 0 kilovolts. And since the insulation is under voltage and a leakage current flows through it, this means that there is both a voltage and a current associated with the insulation. Therefore, as long as there is a voltage and a current associated with the insulation, there must of course be an angle between the insulation voltage and the insulation current, and this angle is the theta angle. Consequently, in all cases, the voltage exists along the length of the cable, whether across the insulation or across the conductor. Hence, the angle phi is associated with the conductor and the conductor current, and therefore the conductor's power factor is cosine phi. But the angle theta is associated with the insulation and the insulation current, and therefore the insulation's power factor is cosine theta. That is why, when we talk about insulation tests, whether in transformers or in cables, we say cosine theta. But the important question is the angle theta, which is associated with the insulation current, always equal to 90 degrees? We said before that the insulation exists between two conductors, whether in cables or in transformers, and therefore the insulation behaves as if it were a capacitor. Accordingly, in the ideal case of a capacitor, that is, when the insulation is perfectly pure and completely free from any impurities, defects, or contaminants, then in this case, the capacitor is ideal, and naturally, the ideal angle of the current inside a capacitor is 90 degrees. However, the usual case is that the insulation is not ideal. This, of course, means the presence of some impurities or contaminants within the insulating material, whether in the solid insulation of cables or within the mineral insulating oil in transformers. Regardless of the percentage or the amount of impurities or contaminants within the insulating material, this will cause the angle of the insulation current to be less than 90 degrees by a certain angle, which we call the delta angle. Accordingly, the greater the value of the delta angle, the greater the amount of impurities and contaminants within the insulating material. And of course, the opposite is also true. If the impurities and contaminants within the insulation are treated or reduced, this means the value of the delta angle will decrease and the value of the theta angle will increase until we reach the ideal case, which is the absence of any impurities or contaminants within the insulating material. In this perfect case, the delta angle equals 0 degrees and the theta angle equals 90 degrees, which represents the ideal condition of insulation, or of a capacitor's insulation in general. Thank you for your attention. See you in the next lecture.